Number two.
You have to find your alpha and omega naught, and
Exactly. And I'm
as
going to
well
call that
as
finding the natural solution.
okay.
And to find the natural solution, what time region do you redraw the circuit in?
Um, Time is greater than zero, so it's the
That's
exact same circuit that we've been analyzing.
well. Let's see. Is it? What's the voltage source?
It's a short.
It is definitely a short. And by the same reasoning, do we need to draw the 5 ohm?
No.
No, because it simplifies. It can combine with that short, and since we don't need to find voltages or currents through it, that makes it simpler. How about that resist? How about the capacitor? What does the capacitor become?
It stays as a capacitor, and
Right. That was a trick question.
the it's the same thing for the inductor as well.
Is
So
it?
I was incorrect as to say that it's the same circuit. It's not.
Right. The components change. Okay. So, but you're absolutely correct in saying we need to find our alpha and we need to find our omega naught, and then we can find our S. And our omega naught is always that. Our S is always that. And our S is one of two things, and it depends if oh boy, I forgot to draw our current. There we go. That's pretty important. And our alpha depends on if our things are in series or in parallel. Which one is it? Ben.
Sir.
Because and just to say why we need to know, it's either equal to R
So for the alpha, we have
L
R over 2 L.
series,
Oh,
or it's 1/2 RC if it's in parallel. And I shouldn't have drawn equals. They're not. Those are definitely not equals. It's two different things. So Ben, what is it? Series are those two devices in series or parallel or both?
so they're in series.
They are.
Oh,
Anyone
actually,
wanna add to
they're
that?
in parallel because there's nothing in between.
Yeah, that's right. They're in both series and parallel. Remember, it's just as another small aside here. Series versus parallel. If it's in series, the currents are equal. And if it's in parallel, the voltages are equal. And for this one, it's both. So you can use either equation, whichever one gives you a good result. Which one gives you a good result?
So the one in series would give you a faster result. Sir.
Not only a faster result, it gives you a result. And what is that result?
So it would be
What is it?
so it's 0 over 2,
That's it.
1 over 4. The 2 them 1 over 4, so 2.
2. Let's do it again. So if we use the series, it's going to be 0 over 2 times whatever that inductor is, which is 1/4. So this is going to be 0. And we can't use the parallel because it gives us 1 over 0. And 1 over 0 isn't infinity. It's not 0. It could be anything at all. It's actually, it could be anywhere from negative infinity to positive infinity. You can kind of see that if you take 1 over x, and if x is really small negative, minus 1 over a million, minus 1 over 10,000, that's negative 10,000. On the other hand, if you're approaching it from the positive side, 1 over positive 10,000, that's positive 10,000. And if you approach it from the imaginary axis, minus 1 over, if it's j times 1 over 10,000, that's going to be j 10,000. You can play the same game if it's approaching 0 from the negative j side. So in that complex plane where this is the real part and this is the imaginary part. 1 over 0, depending upon where you approach it from, can be anywhere in the entire complex plane, anywhere from negative infinity to positive infinity, negative j infinity to positive j infinity. So we just can't, it's just undefined. We just don't know what the heck it is. But we can figure out the rest. This is 1 over the square root of, we've got a quarter times a 16th, and that's 1 over the square root of 64. So that's going to be 8. And before we go any further, if alpha is 0, what does that tell you about how much this wants to damp out? Where are we up to? John, if our alpha is 0, what does this tell us about how much the circuit wants to dampen?
I do not remember what those rules are.
Okay. This is more of an intuition thing than a rule. Alpha says, how much does the circuit want to damp out? If alpha is really big, it really wants to damp very strongly. It's got a tiny resistor. It's dominated by a huge resistance, and it's going to approach its final value, very, very slowly. If omega is really big, it wants to oscillate. And if there's no resistance, it'll oscillate at omega naught frequency. So the fact that we've got a finite omega naught, but we've got no dampening coefficient at all, means that there is nothing in the circuit that wants to dampen its response out. This thing wants to oscillate. It wants to oscillate bad, and nothing's going to stop it. And you're going to see it when you solve for S. So when you solve for S, we get 0 plus or minus the square root of negative 64, which is just J 8.
Sir, are we using J particularly because it's because of like the way that we're analyzing the circuit, or is I incorrect? Are we solely using J for imaginary numbers?
Electrical engineers only use J for imaginary numbers because otherwise they'd get it confused with currents. So mathematicians use I's and electrical engineers use J's. Now we know what omega sub d is. S is always equal to minus alpha plus or minus J omega sub d, and therefore our omega sub d, which we only need to find out if we have imaginary roots, is going to be 8. Now, is this thing underdamped, overdamped, or critically damped?
Underdamped, sir.
Way underdamped. So you just look up the formula for underdamped to find I sub n, and it's going to be equal to just to keep good board technique, I'm going to rewrite my omega sub d up here, and then I'm going to rewrite everything else. Our I sub n is equal to, in general, for an underdamped system, e to the minus alpha times C1 cosine omega sub dt plus C2 sine of omega sub dt. But since our alpha is 0, that just collapses down into some unknown amount of cosine of 8t plus some unknown amount of sine of 8t. And that is our natural solution. Oh, wait, there's 2 unknowns in there. Is that a problem? Should I solve for those unknowns using my initial conditions? What do you think? Who's next? Aiden. Did I miss you the first? I think I skipped over you the first time. Do I need to fix that problem?
Yes, I think you do.
No.
No.
Your natural solution when you're done should always have 2 unknowns in it. Where those unknowns are depend upon if your natural solution is underdamped, critically damped, or overdamped, but they should always have 2 unknowns. And you're going to keep those unknowns there for now. You're not going to take away those unknowns until you do your 3rd step,